Okay, welcome back. I'm sure the webcam is kind of where it should be. Okay, this is 15.5 on parametric surfaces. Okay. So before we have already dealt with parametric vector valued equations, and we kind of got there using parametric curves or parametric equations. We want to go from just curves. So we had these things in space, whatever they did. Um, but they were generally given by some vector valued equation like R of t equals x of t comma y of t, where t is the parameter, right? Um, right now we're dealing with a lot of surfaces, so it would be nice if we can have maybe a parametric form for these surfaces, and that's what we're after in this section. So, in general, sure, we may be given a surface in terms of x and y, so z equals some function of x and y, but now we want to have another form for that surface. And I believe the point is it gives us the option of having more complicated surfaces. Okay, so this time, instead of just having one parameter, we're going to have two parameters. And then, this will be, everything is dependent on these two variables. Okay. Something of that nature. Okay, and of course you could have three variables, z of uv. Okay, well, I guess you would need three variables, right, if it's in space. Okay, so that's our objective for parametric surfaces, and it's sort of like in these sections we'll be able to generate two different integrals for all of our little details and things we need to do. So it does become a little overwhelming with the amount of integrals you're going to be dealing with. But the book is nice enough to usually give you a summary of the integrals at the end of the section. 15.6, I guess, probably has a pretty good summary of integrals if you look in there. Okay. So anyways, without further ado, let's take a look at some of these parametric surfaces now in 15.5. Okay, so section 1, trying to avoid the webcam. It's like right where my pen is. Okay, so I apologize. Parametric surfaces. And our vector valued equation for these guys will look like this. X of uv, y of uv. It's basically just what I just wrote. Z of, or z, as some people like to call z z. We'll look at the first couple problems in the book. For example, number 2. So what's going on in these problems is they give you this parametric surface and they want you to identify what it is. And you'll do these problems because ultimately you want to go in the other direction, right? So they'll give you some sort of surface and you want to generate the vector valued equation for it. Okay, so these give you the basic building blocks towards that understanding. So we have u cosine v, u sine v, and then u. Okay, so it's just a matter of eliminating the parameter. Same sort of deal as what we did probably back in the beginning of parametric equations. So, identify your x. X is u cosine v. Y is u sine v. And then z is equal to u. Right? Whenever you have these trig type components, probably going to have to use one of our trig identities to convert it back into the x, y, z kind of setting. So let's take these guys and rewrite them a little bit. Sorry, I just woke up. I'm kind of All right, so I'm going to rewrite those guys, and then you can see, all right, cosine squared plus sine squared equals 1. So you can create this equation in terms of x, y, and u. So cosine squared is x squared over u squared. Sine squared is y squared over u squared. And from the Pythagorean identities, that must be equal to 1, because cosine squared plus sine squared is equal to 1. And then you could replace u with z, right? So you put a z in there, and then multiply both sides by the z squared. Right now it's u squared. And you end up with x squared plus y squared equals u squared, but u squared, of course, is just z squared, okay? And then you start thinking, all right, this is like a chapter 11 problem where I'm identifying the quadric surface, right? So you could look at the cross sections if you so wish. When z is equal to 0, you get x squared plus y squared is equal to 0. So you just get a point. But if you let z vary, like let z equal 1, and you look at a cross section that's parallel to the xy plane, then you're going to get a circle, right? So as you move out in the negative or the positive z direction, up or down, you're going to have circles that are increasing in radius. Let's look at the other cross sections. So for example, the xz cross section, when you let y equals 0, you're going to get x squared equals z squared. And if you remember your chapter 11 stuff, that's just basically x equals plus or minus z, or vice versa, z equals plus or minus x. And what is that? That's just two diagonal lines through the origin. Okay? And then likewise for yz, you're also going to get the two diagonal lines through the origin. So at the end of the day, what this thing is one of our elliptic cones. So at the cross sections in the z direction are going to be circles, okay? And then they'll get bigger down here, and then you'll have these kind of traces there. So it ends up being a double-headed cone, basically. Okay. The book helps you a lot. So what the book is going to do, I don't know if the webcam is going to like this, but I'll try not to knock it over. It gives you a bunch of options to pick from, and obviously option F is what we're after. So you don't even really need to draw the thing for the answer. It's just F. Okay, but you store this into your memory banks. And if they ask you to create a vector value equation for a cone, you'll be able to using this process in reverse. Okay. Okay. So let's. We kind of just want to knock off those first 6 in the books and make sure we can kind of stomach doing these types of problems. Section number 3. We have u 1/2 u plus v, and then v. Okay, so eliminate the parameter and see what you're dealing with. X is equal to u, y is equal to u plus v over 2, and then z is equal to v. Okay. So plugging x and z into this equation, you can eliminate the u's and v's, and you get y equals x plus z all over 2. Well, and that's, if you forgot, that's just the equation of a plane, and not all that difficult to plot. So if and let's see, I'm not going to be able to do like let x and y equal 0 and then get the intercept, because this thing is going through the origin, the 0, 0, 0. So you can't necessarily plot the points on the axes and then do your little triangle type thing. It's not going to work. So anyways, let's just look at the traces again if you want to, but ultimately it is a plane, and there's only one plane in the book given, and that's B. Okay, so the equation of a plane always has this kind of x, y, z, nothing squared, nothing cubed on it, flavor to it. If you remember the equation, you would need a point and a normal vector. And the equation would be something like a times x minus x1 plus b times y minus y1 plus c times z minus z1. equals 0, right? It's the set of all vectors such that when you dot product with the normal vector to the plane, you get 0, okay? So the normal vector to the plane in this case would be ABC. Okay? So you could rewrite it to look like it's in this form if that's more convincing to you. It'll be x plus z and then minus 2y equals 0. So its normal vector would be 1, 1, negative 2. Okay. And it obviously has an intercept at 0. But okay. Let's look at number 4. And we have r of u v equaling, sorry, I went off the page, r of u v, where is it? U 1/4 v cubed, and then v. Okay. So again, eliminate the parameter. X is u, y is 1/4 v cubed, and z is v. So you'll have y equals 1/4 z cubed as your equation. And there were some questions on the test. It was like, they're going to call this thing a cylinder. Anything that is kind of built by a generating curve in one of the planes is considered a cylinder. So in the YZ plane, you would have this cubic thing. If you rewrote it, z equals, the cube root of 4y, it maybe look a little more, toward what it is. It'll look something like this, right? And the YZ plane, but x then will be varying over all real numbers. So what that means is you have this as your generating curve, and it kind of gets pulled out to create all of the other parts of it. So you end up with a surface, which is kind of like this. Okay? And if you look in the book, the only thing that matches up to that would be A. All right, so that's a cylinder, but not in the traditional sense of a cylinder like a pop can, but this would be A. Okay. All right, 5 then. Oh, where are you? Right, so this one, RUV, is 2 cosine V, cosine U, and then 2 cosine V sine U, and then 2 sine V. Okay. So again, we have some trigonometric functions, and that kind of suggests that you better go to your trig identities if you want to pull this off. And excuse me, in particular, let's see what happens when we go x squared plus y squared or some variation of that. So you get 4 cosine squared v cosine squared u plus 4 cosine squared v sine squared u, and that's x squared plus y squared right there. Okay. So what? Well, I can factor out the 4 cosine squared v, cosine squared v, and you'd be left with cosine squared u plus sine squared u, which is just 1. Okay, and then that would be x squared plus y squared. And you want to eliminate the parameter, right? You want to eliminate this v. So we can kind of use this in order to eliminate this, because cosine squared is just what? Well, that's 1 minus sine squared v. That equals x squared plus y squared. And then I want to, z right now is equal to 2 sine v. So if I divide both sides by 2, so z is equal to 2 sine v, that just comes from this component. If I divide both sides by 2, I get sine of v equals z over 2. And then if I square both sides, I get sine squared v is equal to z over 4, z squared over 4, excuse me. Okay, so you could plop that into there to eliminate the v parameter, and you get 4 times 1 minus z squared over 4 equals x squared plus y squared. And then distribute the 4, and you get 4 minus z squared equals x squared plus y squared. And now it's looking really familiar, right? That's just a sphere. X squared plus y squared plus z squared equals 4. A sphere with radius 2. Okay, and if you look in the book, there's only one sphere given, it's D. Let's look at one more. So number 6. I didn't do number 1 because it's not obvious, but you could process of elimination kind of figure out, and really we're not going to need to do that one anyways, so you do it on your own, ain't going to hurt you. So 4 cosine u, 4 sine u, and then v. Okay. So, another one of these trig thingamajigs. So, x equals 4 cosine u. Solve for cosine u. So cosine of u is going to be x over 4. Likewise, sine of u is going to be y over 4. So cosine squared plus sine squared is equal to 1. That's equivalent to saying x squared over 16 plus y squared over 16 is equal to 1. And that's pretty much it, right? So that's the generating curve here. So it's the traditional type cylinder. So z is allowed to vary over the real numbers. So at every cross section of z, you're going to have a circle radius 1. And what's the result of that? Well, it's just a cylinder, okay, in space. Alrighty then. That's pretty much, that gives you some grounding. Now we want to go kind of in the other direction. So they're going to be giving you rectangular coordinating equation, and they want you to convert it into a vector valued function in terms of u's and v's. So going in the other direction, parametric, finding the parametric equation, I guess. Finding r of u comma v, right? All right. This is number 21. Is an easy one, supposedly. Z equals y. So don't overthink these if you can get away with it. Just let y equal u or v. And what do you get for those two components? Well, if y is v, then z must also be v. And then you're just letting x vary over the real numbers. And what you have is a plane. Okay? These are a little like riding a bike. I literally don't think about the geometry of it. I just get experience points, by doing the homework, and then apply the experience to the problems. Okay? And it's just that. It's kind of, how am I going to explain this to people? That's it. I went in there, I did the homework, I did the problems, and now it's in my brain. Cone y equals square root of 4x squared plus 9z squared. Okay, so again, the experience. If you think about what we did already, we have a formula for a cone. Kind of, you probably would never came up with this on your own, but that's it. The only difference between this thingamajig and this thingamajig is this thingamajig has a square root on it. Okay, so you need to be careful about your, I guess, the range settings on your y value. Okay? Otherwise, I think we can just kind of leech off of the problem here and say, all right, I'm going to let so this was x squared plus y squared equals z squared. In this problem, it's if you squared both sides, you get y squared equals 4x squared plus 9z squared. Okay, so this component is like the x component here. So I want to let 4x equal the u cosine v, and then this 9z component here is like this y squared component here. So I'm going to let whatever the heck the thing is squared equal the u sine v. Okay, so the sorry, this should be 2x, right? And then this will be 3z equals the u sine v. Okay, sorry, on that page. Right, and then you just let the other guy equal u, right? So then let y equal u. Right? The only difference between, then again, the only difference between that thing and this thing is that thing is just the top half, right? So you're kind of excluding the bottom part, and you can deal with that issue by restricting the u values to be positive, or if you did it the other way around, you know, the v values to be positive. So I'll just say this has to be greater than or equal to 0, and that should do it. Okay, so my vector valued function here, I'm going to have to divide both sides by 2 on this thing, so you get u cosine v all over 2, and then u, and then u sine v all over 3. Okay. Right, and you know, it's not going to be that we're sitting around needing to do this all day long, so you don't need to be a master of this. It's not something you put on your resume. Just be able to get in there and just get in there and get your feet dirty and get your hands dirty or whatever they say. All right, let's look at another one. Oh, well, just one. You can always kind of do a cheapskate version of these if you have no clue. You can just let u equal x and v equal y. Sorry, the webcam thing's getting in the way. So another way of pulling this off is to let u equal x, v equal z, and then just replace x and z with u's and v's and let y equal this thing in your vector valued equation. So you could always write it like that if all else fails. So you could write u and then square root of 4u squared plus 9v squared, and then v. Okay, so that's another option you have in your toolkit, just by the way. All right, I think that's enough. You know, okay. All right. Now we need to kind of redo section 14.5, but now in terms of parametric surfaces instead of just regular functions. So 14.5, I'm looking it up in my book, was all about surface area. Okay, so recall 14.5, and in order to get surface area, we needed to do some stuff. So it's kind of the development here. Just recall what we did. So we had some sort of surface S here in space over top of some region A, or we'll call it R. All right. And then what we did was sort of section up the region R into a bunch of little areas. So, you know, this would be our change in X dimension over here, and then over here you'd have some change in Y. And then we would take a particular point in R and look at the sort of vectors attached at that point. The vectors were created by looking at the partial derivatives of the surface function, and then we would figure out the area of little tangent planes to that to this surface using the cross product, the magnitude of the cross product of these particular vectors for that particular point. And you'd call that something like delta change in t sub I for the area of the tangent planes. And we said that was approximately going to be equal to little actual parts of the surface. This change in t sub I, the result of that, it looked like a disco ball, right? You'd have all these little kind of rectangles on it. And then our Riemann man would run through and add up all of those things as the change in x, change in y, as the norm of these little boxes goes to 0, and then we would end up with our integral over this region for the surface area. Okay, and then the book wrote it like this. It seems like it should be like this, but well, I don't know. I think maybe the book made a mistake there. I'm not 100% sure, but they're writing it like that. And then we figured out the formula based off that cross product and stuff like that was the double integral over the region R of the square root of the partial of f with respect to x squared plus the partial of f with respect to y squared plus 1, and then dA. Okay, so that was our working kind of definition for finding surface area if you're given the surface as some sort of function. Okay, and that's all 14.5 stuff, so you can go back and watch my video or whatever you need to do there. Okay. All right, so 14.5. Off the top of my head, that's kind of the deal. We want to do the same job now with parametric surfaces. So there's going to be some fundamental differences. In particular, we don't have this function for the surface. So what we'll end up having to do is kind of leaving this in terms of the cross product. Okay, so you'll see this magnitude of the cross product of these vectors, and we'll just have to kind of leave it in there. We have to do some development here. We have to figure out how to find a tangent plane to the surface given a parametric equation. And then we'll talk about the normal vectors to the surface, because you always need a normal vector in order to get the equation of the plane. And then finally, we'll generate this new integral, but now in terms of the parametric equation. Okay, so it's basically 14.5 again, but now in this new setting. So let's take a look. First, we'll just work with getting the equation of the tangent plane, and for that, we'll need the normal vector to the surface. Okay, so we're going to be given, again, this R of u comma v thingamajig. And what we're going to be using to form these vectors, like we did back here, are partial derivatives of r with respect to u and then with respect to v. Okay, so we need then r, the partial derivative of r with respect to u, which will just be taking the derivatives of the components with respect to u. So we have the partial of x with respect to u, partial y with respect to u, etc. And then this thing, which would just be the partial of x with respect to v, and then the partial of y with respect to v, and then the partial of z with respect to v. Okay. And then we want to get these vectors on the surface. Okay, right. So we're going to be moving from the UV plane, and so we have some region here that's sectioned up into a bunch of change and U's and changes in V's. Okay. So what we're thinking of right now is, what exactly does this mean geometrically? Okay, so you have to imagine that this UV plane is kind of like this plane, this XY plane, but it's not. Okay, it's not the XY plane, but we're some other plane that's not really visually attached to where we end up. Every one of these guys is being transferred onto the surface in the XYZ plane. So here's my surface in the XYZ plane. Okay. And so what does that mean to have a partial derivative in the direction of u? So that means I've kind of held one variable constant. So I've held the v variable constant, and I'm letting u vary, right? So I've said I've sort of set, and I don't know which way it's going once it gets mapped onto the surface, right? So it could be, uh, so I have to be careful, a little bit careful here. Um, Partial derivative with respect to u is holding v constant. So maybe this is um, the line at v sub 0, right? And then when I put it into this function, it's going to be mapped onto this curve here, right? And then if I take a point um, on this curve, the partial derivative with respect to u will kind of tell me the direction, or give me the slope of this guy right here. Okay, and then let's say I hold v constant and let u vary. Maybe I'll get some other curve that looks like this on the surface, and then it'll have an associated vector right here. Okay. You could do that all over the place, and eventually what would happen is you get kind of a plane type deal here. So if you just take all these curves, I guess, I don't know, and you end up with a plane of vectors if you were to take the so not necessarily just u and v, I guess, but you would have maybe a directional derivative and this. I don't know. I'm getting off topic, so let's shut up. Anyways, so that's kind of the idea. You're going from here to here. You're getting these curves on this object, but they may not be aligned with the x and y plane. That's the only sort of danger that I can imagine here when you're constructing these vectors. Okay, so that's kind of the idea of the partial derivative in the direction of u and the partial derivative in the direction of v. I'll just leave it at that. I shouldn't have drawn all these extra vectors on there. It's just those two vectors is what we're interested in. Okay. And then if we take the cross product of those two vectors, what we're going to get is a normal vector, which should be perpendicular to the surface. Okay, so it should be the normal vector we need for the tangent plane. Right. So that's kind of our first stop here, the normal vector to the surface. And we'll just basically take the cross product of this partial derivative in the direction of u with the partial derivative in the direction of v. Okay. And then to get the tangent plane, we can actually do one of those. So let's look at number 37. And we have r of u comma v equals 2u cosine v comma 3u sine v comma u squared, excuse me. And we want to know the equation of the tangent plane at the point 0, 6, 4. Okay. All right. One thing we will need then is the u and v that give us these values. So if u squared gives 4, then it's either u is either plus or minus 2. Okay. Then we kind of can pick some points maybe where we'll work with the cosine and the sine. So I want the cosine to be 0, but the sine to be 6. So if I use positive 2, this will be 6. And then if I let v equal pi over 2, I'll get this one to come out 0. So that's kind of what I want. I want v to equal pi over 2, and then u will equal 2. Okay. Alrighty then. I need the partial derivatives of this. So r with respect to u is going to be 2 cosine v, comma 3 sine v, comma 2u. And then r with respect to v is going to be negative 2u sine v, and then 3u cosine v, and then 0. And then I need the cross product, so I'm just going to cheat a little bit here and go ijk. And so this will give me my normal vector I need for the plane. So if I cover that stuff up and find this determinant. It'll be 0 minus 6u minus 6u cosine v. Then cover those two up and get the the cross there. So that'll be negative 0 minus negative 4u squared sine v. And so I have a feeling this first one should have been u squared as well. Okay. At the end of the day, this will be then negative 4u squared sine v. Okay. And then cover up the last one. So this would be 6u cosine squared v. And then minus, which will become plus 6u sine squared v. So you could factor out the 6u, and then you get sine squared plus cosine squared again, which is just 1. So it'll settle into this formula. Okay, so now I need my normal vector. I saw my little n here. I'm going to input these values into this formula. Okay, so I'll get negative 6 times u squared. Well, cosine of pi over 2 is just 0, so this first component is 0. And then the second one, what do I have? 4 times 4, 16, negative 16. And then the third guy, 2 times 6 is 12. And I only need the direction, so to make my math a little nicer, I'm just going to kind of multiply through by 1/4. So I get 0, negative 4, 3 as my normal vector. And then finally, the equation of the plane is just the dot product of this with the vector, any vector created in conjunction with this point here. So that would be 0 times x minus 0 minus 4 times y minus 6, and then plus 3 times z minus 4. Okay, and that'll equal 0. So at the end of the day, negative 4y plus 24 plus 3z minus 12 is 0. And then combine like terms, so negative 4y plus 3z equals negative 12. Okay. Okay, so we can, given a parametric valued function for a surface, parametric valued equation for a surface, we can go ahead then and find a tangent plane to the surface. So if we can find tangent planes, then the next step is to kind of, all right, let's section up one of these surfaces into a bunch of little tangent planes, and then add up the areas of all these little tangent planes, and that will give us the surface area. Okay, and then eventually we'll be able to maybe attach some other value, some other factor to that, and sum up all that junk, and it'll give us pretty much whatever we want to use it for. Okay. One of our applications then later will be flux, I think. So the amount of stuff going in and out of a surface. Okay, so that's our next goal, finding the area of a parametric surface. So some of the questions on the test were find the area, and what they're really meaning is find the surface area. They don't mean find the volume or anything. The area of a parametric surface. So again, there's kind of this issue that we're not exactly going, taking this XY plane region and then mapping it to the surface. No, it's you're starting in the UV plane and then mapping all that junk onto the surface. So you're sort of bypassing this region down here, right? And maybe that causes some issues, but so long as the vector value equation isn't I don't know, doesn't have any sort of issues with it, it works out. And for us, you don't really have to worry about any of the minor details. But again, the idea is we have some region, which the book is going to call D, in the UV plane, and we're sectioning it up into a bunch of little boxes, change in u over here, and then some sort of change in v over here. Okay? And then we're mapping all of this junk onto some surface over here. Okay? And the XYZ plane. So this is our surface S, and I don't know how the U lines and the V lines match up exactly. Maybe they're kind of like this. Okay. But the point is, we want to create these two vectors that we use as kind of the borders of the little tangent planes over here, right? So we're going to get these two vectors and then find their cross product, and that gives us the area of this little plane here, this little tangent plane. We do that all over the surface, and then add it all up, and that's our surface area. So, and here, if we take this particular point here to be u sub I comma v sub I, and then we go r of u sub I comma v sub I, and we're putting that point right here. Okay? We want to create some vectors on this surface. So the vectors will create, let's call them R1 and R2. Right? So we'll say R1 is going to be equal to just the difference of these points under this transformation. Okay, so this point is certainly u sub I comma v sub I. This point up here is going to be u sub I comma v sub I plus change in v, and then this point over here is going to be u sub I plus change in u comma v. Right? So to form this vector, what we're going to kind of do is put these points into this function, and then find use the difference of those two as the vector over here. Okay? So well, I'm saying do this. R of u sub I plus change in u comma v, so r of this point, minus r of this point, so r of u sub I comma v sub I, and then the other vector will be r of this point up here minus r of this point down here. Okay, so R2 is r of u sub I comma v plus change in v, v sub I plus change in v, minus r of u sub I comma v sub I. Okay, and then these things should look kind of familiar. They kind of look like difference quotients from partial derivatives, but here the partial derivatives are u with respect to u and respect to v. Right? All you would need is quotient bar, and then put change in u underneath, and then this would be the partial derivative in the direction of u. Right? So this is approximately equal to the partial derivative in the direction of u times change in u, because we don't have that all over change in u part down here. Okay, and then likewise, this thing is just r, the partial derivative with respect to v times change in v, right? And then, right, we got our vectors, and we just take the cross product, and then this will lead to the following approximation for these little surface increments. It'll lead to an approximation of those little surface increments with these tangent planes, right? So the tangent planes aren't exactly the same thing as elements on the surface. The surface elements would be kind of curvy, right? They would kind of be like this or something. The tangent planes are literally, there's no curve to them. So you have to kind of state, all right, this is an approximation, and so what are the change in t sub i's then? That's just going to be the cross product of these two things. So r sub u change in u crossed with r sub v change in v, and at the end of the day, what does that equal? That just equals the magnitude of R sub u cross R sub v, change in u, change in v, right? And then this thing is going to be the thing that we're going to dump in our integral in place of the square root of fx squared plus fy squared plus 1 dx dy. Okay, it's basically just the parametric version of this thing here. Okay, so when we take the sum of these things, we get these, this sum of these tangent planes, and then if you take the limit, we'll get our integral. So the double integral over the surface S of the surface area elements, and then our working definition, it's a double integral over this region D, which is in the UV plane, which is why they use D instead of R. This kind of makes me wonder they made a mistake in the book. They're using R over here, and I think they should have been using S. But oh well. So the working definition, then we have this part. So R U cross RV dA, okay, for our surface area of these things, right? Okay. If you let Z, one note the book makes is that you can kind of connect these two. If you just let, if you have Z equals, if Z equals f of x comma y, and then you rewrite your vector valued equation R of u comma v as u comma v comma f of u comma v, you're going to be able to use this. Okay, so it's almost like you don't even have to use this ever. You can always just remember this formula if you're forced to memorize all these formulas for whatever reason. You can always play that kind of game. Okay. Okay, I don't know. So let's look at a problem in the book. This is number 41, and we're given some vector valued equation, R of uv equals a cosine u, a sine u, and then v, and we're restricting the u to be from 0 to 2 pi, and then we're restricting the v to be from 0 to b. Okay, so what is this thing? First off, maybe that's a natural place to start. X is equal to a cosine u, so cosine u is equal to x over a, and then y is equal to a sine u, so sine u is equal to y over a, and then cosine squared plus sine squared is equal to 1. So what we have is a circle with radius a, right, as our generating curve in the xy plane, and then z is varying from 0 to b. So ultimately, the picture in the xyz plane in space, we have just our generating curve there, and then we're varying the height value from 0 to b. So if we have some point 0, 0, b up here, our cylinder is going all the way up to that point. Okay, so there's our thing. Right. So we want to find the surface area of this guy, and so it's just a matter of dumping everything into our formula for surface area. So it's the double integral over this region and the UV plane of the cross product of RU and RV dA. Right. So find this cross product. So RU is, respect to u, it's negative a sine u, and then a cosine u, and then 0. And then RV is 0, 0, 1. Okay, and then we need the cross products. I'm going to cheat a little bit and just write it like this. All right, and then cover those guys up. So it's A cosine U, comma, negative, negative of negative A sine U minus 0. So it's going to be A sine U. And then the last guy is 0. Okay. All right, I need the magnitude of that then for my integral. So the magnitude of that is just the square root of the sum of the components squared. So I have A squared cosine squared U plus A squared sine squared U plus 0. Okay? I can factor out the A squared. You get A squared times cosine squared plus sine squared. That's just 1 again. So my magnitude of R cross RU cross RV is A. So I can dump that into my integral. So what is it? A. And then I'm integrating over this region D in the UV plane. So I'm not really integrating over the circle, you know. It's this region here. So the U variable is going from 0 to 2 pi. So I'm going to put that on my y-axis. And then the V variable is going from 0 to B. So it's basically this square region I'm integrating over. So on the bounds of my integral, I'm going to go sort of the du and then dv. So u is varying. Whoops, I want to go the other way. I want to go dv du, sorry. So v is varying from 0 to b. Right, and then u is going from 0 to 2 pi. Right, so 0 to b, and then 0 to 2 pi. Okay. Whoops, I went off the screen there. There it is. Okay. Right, so I'm just thinking in my head, make sure it's right. It's the wrong order. I apologize. So up here this would be the U, and then this would be the V. So if I go with my running man in this direction, yeah, I'm going to get the same answer whatever way I do it. But the running man, if he's going in this direction, the V is like the x-axis, right? So I'm going curve the curve. That means 0 to 2 pi. So let me rewrite this integral. And I'm going du and then dv, right? And I have an a in here. So if I go curve the curve, that's 0 to 2 pi. And then point the point is 0 to b. Okay, I'm sorry. I just got lazy there. I know what the answer is. Give me a break, you know. So the integral is, all right, so I have au now. And then I have to evaluate that from 0 to 2 pi. And then we got a dv. And so evaluate it, it'll be 2 pi a minus 0 a, which is just 2 pi a dv. And then integrate that with respect to v. So 2 pi a v, and evaluate that from 0 to b. And that's just going to be 2 pi ab. Okay. So there's that. Yeah, it's a lot to stomach, but you know. All this junk, I was just watching videos last night. So that 3 blue, 2 brown guy, he used to work for Khan Academy or something like that. He did all kinds of videos there. So I was watching the curl and divergence videos. It gives a good interpretation of, well, I don't know any better, but I think it's a good interpretation of curl and divergence, physical interpretations of those operators. So I say go watch his videos. But one thing I found interesting is kind of the fact that all Maxwell's equations are written in terms of divergence and stuff like that. These formulas that you're learning right now here. So if you go into like more physics applications, I think you're going to see a lot of this stuff. Okay, I've never really studied physics, but I think it's especially for an engineer. I think that kind of stuff would be very important for you. So, keep chugging away. Don't give up faith. We're here for you during the pandemic. And all right, good luck.